Yeah.
Okay, morning everyone. So today I'm going to talk finally about R trees and lambda trees. So lambda is going to stay for ordered abelian group. Let me recall that what is an ordered abelian group? We have some background echo. So
Maybe people should mute themselves if they are not muted.
yeah, if you could mute yourselves. Okay, so ordered abelian group, this means that any two elements are comparable, and for any other element, so the order is preserved with respect to addition. Like examples, Archimedean order, real numbers, like or integers, and non-Archimedean order. So Archimedean means that for any two elements A and B, there is a number, natural number n, such that NA is greater than B. Now, non-Archimedean, for example, Z square with right lexicographic order. So the pair AB less than CD if either B less than D or B equals to D and A less than C. So it's right lexicographic order. And so this is a non-Archimedean case. So there are elements which are infinitely smaller than other elements. Like, for example, the pair like 0, 1, no, 1, 0, we cannot multiply by a natural number to become larger than the pair 0, 1. Like the pair 0, 1 is infinitely larger than 1, 0. One can like graphically, one can like show this like this. So like everything is in this row is infinitely larger than everything is in the row below. Like so the right component is the larger one. Or like in a one-dimensional picture, you can think about copies of integers one after the other. Now, what is a lambda tree? In 85, Morgan and Shallin defined lambda trees. And the definition, I'm going to give a definition for a lambda tree. But you can also think about reals, about R tree. It's basically the same definition, like if for lambda you substitute R, you have a definition of a real tree. So it's a metric space. Now metric is in lambda then, which is geodesic metric space. If two segments intersect in a single point, which is end point of both, so then their union is a segment. And intersection of two segments with a common endpoint, something like this, intersection, is also a segment. So there are tree-like properties. So when it is, you can, like in the case of real numbers, R3, you can think simply about like zero hyperbolic metric space. And then there is a big paper like by Alperin and Bass, so that's where the theory of lambda trees was developed. And there is also Chiswell's book on lambda trees, which is called Lambda Trees. And so basically the main question is like find the, it still is, find the group theoretic information which is carried by an action on a lambda tree. So suppose we have a finitely generated group and we know that it acts on a lambda tree. What kind of actions, in what kind of actions can we like say something about the group? Like, so basically for simplicial trees, there is Bass-Sir theory. Simplicial trees are Z trees. And so one wants to generalize it to arbitrary lambda trees somehow. Now let me talk a little bit before, like for R trees, there are results and there is a complete description of groups, finitely generated groups acting freely on R trees, so with trivial stabilizers. In case of simplicial trees, these are just free groups, but in case of R trees, this is more interesting. groups. But let me just tell a couple of words about where R3s arise. So, okay, what is the Gromov-Hausdorff limit of a sequence of isometric action of group on negatively curved space? Now, let me first say, so roughly speaking, we say that a sequence of metric spaces converges to a space sequence xn of metric spaces converges to a space x if for every r, the balls of radius r in xn centered at some fixed point converges compact metric spaces to a ball of radius r in x. So, like more precisely, so these are, we have a sequence of metric spaces, so space, metric, and some fixed point in each space, right? And so it converges to a point at space x with metric d and point p, if for every r and epsilon, there exists number n such that for n greater or equal than n, we could find a function such that balls of radius r in Rn, function from these balls into x, such that the point is mapped into this fixed point P. For every elements x, y in the ball of radius r in Xn, the distance between the image, the distance between them in Xn and the difference between distance between them in Xn and the images in X is less than epsilon, and the epsilon neighborhood of the image of F contains the ball of radius r minus epsilon, the point P. So again, like roughly speaking, so the ball of radius r centered at some fixed points converge to a ball of radius r and x for any r. And there is a Poulin theorem which says that so if you have a sequence of delta I hyperbolic spaces and the limit, lower limit of this deltas is 0, then, and if you have a countable group which isometrically acts on xi's, and suppose that there is a base point in each xi, and such that for every finite subset P of H, the sets of geodesics between the images of xi under P form a sequence of totally bounded metric spaces, then there is a subsequence converges in this Gromov-Hausdorff topology to delta infinity hyperbolic space, basically to 0 hyperbolic space, endowed with the left isometric action of H. So if we have a group, countable group acting like nicely on delta hyperbolic metric spaces, and if the limit of deltas is 0, then this group, this action converges to the action of this group on 0 hyperbolic metric space, which is an R3. So basically R3s occur as limits of actions of groups on hyperbolic spaces. Now let me give you an example which is kind of okay, so first this theorem, and then I'll give an example which is close to my heart. Like this is from Bistvina's survey, R3s in geometry, topology, and group theory. So suppose we have a sequence of convergent sequence of based G spaces, so Gx, the spaces xi. Then there exists delta, and there exists delta such that for every xi is delta hyperbolic, and there exists element G in the group such that the sequence, so the distance between the base point and like the image of the base point under the action of this element G is unbounded. So there are elements which take the base points further and further and further in the spaces. Then there is a based G3 and isometric action of the group G by isometries. Now, when we say that group acts on these metric spaces, it will always mean action by isometries on this R3T, and such that the sequence of these converges spaces and the action converges to this R3. And like an example which is close to my heart. So this is related to equations and groups. So take a free group of rank K and consider its Cayley graph. Consider Cayley graph, which is a tree, right? So Cayley graph of a free group, it's a tree. I'm just drawing the Cayley graph of a free group with two generators. Okay, now, and take some group, M generated group, some group, and consider homomorphisms from this group into Fk. So consider, okay, now if you have a homomorphism from G to Fk, then G acts on Xk like this. So this homomorphism H. So the action basically the action is going to be like on the point, like points of the graph are elements of the free group, right? So if X is a point of the graph, we just multiply this point on the left, we just move this point on the left by H of G, by the image of element G under the homomorphism H. Right, so for example, if H takes G1 into, let's say, A inverse, then we move a point, like this point is going to be moved here. Okay, now suppose we have a sequence of these homomorphisms. Suppose we have that's maybe complicated, but maybe, maybe I don't go into details. Suppose we have a sequence of homomorphisms. Now, all this, so the group G acts through each homomorphism. So we have a sequence of homomorphisms now. Suppose they are not conjugate. And suppose like they are different enough. Like they take, for example, identity element Hn of Gi of the identity element is unrestricted. So like Hn takes Gi's into longer and longer elements. This happens, for example, if you denote group G, suppose it is generated by G1 Gm, and we take some relations between, it has some relations, we can think that we are solving equations, that we are solving the system of equations R of G1 Gm in a free group. So elements G1, these are going to be homomorphisms of G into F. Okay, so it's basically solutions of the system R of G1 Gm. And if the solutions are different, if there are infinitely many of them, if they are different and they are not conjugate, then what we can do? So all these spaces, it's basically going to be the same space, like the sequence of spaces, let's say Xn, they all are just trees. Moreover, so since this is unrestricted, we can, so they're trees, so there's zero hyperbolic. the sequences are unrestricted, so we can normalize the metric. Like we can divide the metric in each xn. We can divide it by a maximum of hn of like 1, by the maximum length of the images of generators. And then by the previous theorem, by this theorem, there is a base G3. So G is this group. So there is a base G3 with as a metric action of G. So like this action of G on the Cayley graphs of a free group converges to the action of G on an R3, like this way. And since like it is a good action, it's actually a stable action, and we know a lot about like R3s and stable groups acting stably on R3s. So this is like one of the examples. This is, for example, how R3s are used in model theory of a free group, like in the solution of Tarski's problem. Like it's you deal with solutions of equations, so you deal with the homomorphisms of groups into a free group, and the sequence of these homomorphisms converges to the action of the group on the R3. So I skip these slides because, and actually Seller's definition, like if you take the kernel of this action, so it's a set of all elements of which basically the kernel of the action which send everything into itself. And we can take a quotient of, we can consider the quotient of the group G over this kernel. And so this is what's called a limit group. Limit groups are exactly finitely generated, fully residually free groups, which we consider to be the Alexei-Mesnikov. So this is a very interesting class of groups. So this group is so a group is fully residually free if for any finite number of non-trivial elements there is a homomorphism to a free group sending these non-trivial elements to non-trivial elements. So it's a class of groups started by Benjamin Baums like long time ago, but like these groups are what is nice about them? They turned out to be models of the universal theory of a free group. Like these are exactly models of the universal theory of free group. They have a good structure. They have good structure in terms of like HNN extensions. They can be obtained from a free group by a sequence of very nice HNN extensions. Like I spoke about HNN extensions yesterday. So they have nice splittings. And they're the same thing as the limit groups, as limits of actions of groups on a limit 3, like defined like this. So it's kind of in limit groups, everything comes together, like actions on real trees. It's geometry, right? Logic, so they're models of the universal theory of a free group. And actually algebraic geometry, because those groups are coordinate groups of irreducible algebraic varieties over a free group. Like over a free group, there is key topology, there are algebraic varieties, there are reducible algebraic varieties, like in commutative algebraic geometry. And in commutative algebraic geometry, one has coordinate rings. In here, you have coordinate groups. So coordinate groups of reducible algebraic varieties over a free group are exactly these limit groups. So like, and this how R3s appear like in model theory of a free group. So they very like naturally appear there. And they also, R3s appear in Thurston theory, but like this model theory of a free group is more close to like to me, to my interests. Okay, so now what is known about R-free groups? So groups acting freely on R3s, I will call them R-free groups. So R-free groups are they were completely described in the case of when they act freely. So when stabilizer of every point is trivial. So finitely generated, this is called Reeves theorem. But Reeves actually never proved it, but Reeves gave a talk in some conference kind of describing how the theorem should be proved. And it was proved by two teams, Gabriele with Poulen in 94 and Bistvina and Fein in 95. Like also what is interesting about like Reeves method and what was used here. So they use the same, this is now called Reeves machine. But actually Reeves machine, it is the same thing as Makhanin-Razborov process, which solves equations in a free group. Like as I said before, I mean, these things are somehow, these things are very similar in nature, like actions on R3s and solving equations in a free group. And so the same process which solves equations in a free group was used to prove the theorem about free actions on the group, finitely generated group on an R3. So a finitely generated group acts freely on an R3 if and only if it is a free product of surface groups, except for the non-orientable surfaces of genus 1, 2, and 3, and free abelian groups of finite rank. So, so it's a free product of free abelian groups of finite rank and closed surface groups. Like basically have tori and closed surface groups except non-orientable of genus 1, 2, and 3. So very nice description, and also it shows that so what is involved in the description. So there are free abelian groups, like free products, so splitting as free products, and also like all the surfaces that we have seen, they have a lot of splittings as amalgamated product or H&N extensions. It's actually this is a thing, like when we have an arbitrary lambda free group, like what is involved? It's highly splittable. So there are many ways to represent it, usually as an amalgamated product or H&N extension or a free product, except that there are free abelian groups, free abelian subgroups, which are not splittable. But so here it's like in the case of free action on an R3, we just have a free product of surface groups and free abelian groups of finite rank. Bistvina and Fein actually, they describe so-called stable actions. They describe groups that have a stable action. So what is stable action? So if the group acts isometrically on an R3T, a sub-tree is non-degenerate if contains more than one point. A non-degenerate sub-tree is said to be stable with respect to the action if for every non-degenerate sub-tree T2 of T1, the fixed points, I mean, elements which fix T1 are the same as elements which fix T2. So like there is a smallest subtree such that elements which fix the subtree already are the same as elements which fix any proper subtree of it. So it's a set of points-wise stabilizer of T1 is the same as a set of points-wise stabilizer of T2. And the group action on T is stable if it is non-trivial, minimal, there is no smaller invariant, G-invariant subtree, non-trivial, minimal, and every non-degenerate tree in T contains a stable subtree. So every non-degenerate tree contains a stable subtree. So this is a stable action, and Bistvina and Fein actually describe stable actions in terms of fundamental groups, they describe groups which have stable actions on an R3. And they describe them in terms of fundamental group of graph of groups. Actually, I spoke yesterday about fundamental group of graph of groups. So this is a graph of groups, and they have like abelian vertex groups. They have surface with boundary vertex groups, and they have some, so like other, like the vertex group. So the theorem can be formulated, this is between and Fein, that if G is a finitely presented group with a stable action on an R3, then either G splits as an extension of E bicyclic, or over an extension E bicyclic. So splits over, this means that the H group is E fixes an arc and E is extended bicyclic. So the H groups in this graph of groups, they are like this. Or T is a line. In this case, G splits over an extension of the kernel of the action by a free abelian group. So it's basically it is a fundamental group of graph of groups with free abelian H groups, something like this. Right, so this is stable actions. And now, in the time which I have, I'd like to talk about arbitrary lambda trees and our results on lambda trees. So these are some properties of groups acting freely on lambda trees. Lambda is an arbitrary free abelian group. Just lambda, just free abelian group. So the class of lambda free groups, but we talk about groups acting freely. We only talk about these actions because stability and so on is becoming too complicated when you don't know lambda, when lambda is just, when all you know is that it is just some other abelian group. So the class of lambda free groups is closed under taking subgroups and free products. This is kind of subgroups. Certainly, if the group acts freely, then the subgroup also acts freely on the same lambda tree. Now, lambda free groups are torsion free. Lambda free groups have the so-called CSA property. This comes from conjugate separated abelian. So maximal abelian subgroups are more normal. Like the intersection of if A1 and A2 are maximal abelian subgroups, then no, it's like this. So A1G intersects trivially with A1 unless G, so if G does not belong to A1 for maximal abelian subgroups. So if G belongs to A1, then certainly the conjugate is the same as A1 because it is an abelian group. But if it does not, then it intersects trivially. So this is more normality, maximal abelian subgroups. We call it CSA property. Now, commutativity is a transitive relation on a set of non-trivial elements. This is basically what it means, that the centralizers of elements are commutative, are abelian. The commutativity is a transitive relation on the set of non-trivial elements. If A commutes with B, B non-trivial, and B commutes with C, then A commutes with C. And then this means exactly that the centralizer of non-trivial element is an abelian group, because these are all elements which commute with some element A, and therefore they all commute with each other. Now also, any to generate a subgroup of a lambda free group is a free or free abelian. So these are kind of simple properties. There is a book by Jan Chiswell, it's called Lambda Trees, where this is all summarized. And there is our survey with Alexei Mesnikov and Denis Serbin. Now, basically, Alperin and Bass, so they had this influential paper, and so they posed a problem, describe finitely generated, or at least finitely presented lambda free groups. Again, lambda free groups are groups acting freely on lambda trees. Now, describe means describe in the standard group theoretic terms. Now, what we proved with Alexei and Denis Serbin, basically we gave a description in the case of finitely presented group. So every finitely presented lambda free group is actually Rn free for some n, where and R is real numbers. So it's R to the n. So it is a group of tuples, n tuples of real numbers, ordered lexicographically. So it's a lot of nice things about this. First, this means in the case of finitely represented groups, we can forget about lambda. Like we actually have like Rn groups, and we know a lot about groups acting freely on Rn trees. And again, we know a lot in terms of free constructions, amalgamated products, and H&N extensions. Like there is a Girardelli results of 2003 that finitely generated freely indecomposable. I mean, free product preserves the action on Rn3. Like if you take two groups which acts freely on lambda 3, then the free product does the same thing. So a finitely generated freely indecomposable Rn free group is isomorphic to the fundamental group of a finite graph of groups, where each vertex group is finitely generated Rn-1 free, and each H group is cyclic. So there is a hierarchical, basically, we start with, what we start with? We start with a group acting freely on R3, right? Which is a free product of surface groups and free abelian groups. And then we can take a fundamental group of graph of groups, where in the vertices we have this like surface groups or free abelian groups. H groups are cyclic. And okay, get to the second floor. And then like they have groups. This is a construction of R square groups, R square free groups. And then we can like continue this hierarchy. So these Rn free groups are built hierarchically. Now this theorem, I mean, it is only in one direction. So if you have an Rn free group, then it is like this. Not every group obtained by this construction is Rn free. Now, but still, I mean, we actually have a theorem with necessary and sufficient condition, but only for so-called regular actions, which I won't mention now. Okay, now, but as a corollary, what we have, that finitely generated Rn free group is hyperbolic relative to abelian subgroups. So it is toral, what is called toral relatively hyperbolics. Now also notice that Zn free groups are Rn free, just the same action, like consider instead of Z to the n, consider just R to the n and have the same action. We did a lot of work on Zn free groups. Like Zn, it is integers, Z to the n, ordered lexicographically also. Like, for example, we proved that finitely generated fully residually free groups, the same as limit groups, right? I just defined them, are Zn free. So they are not only, they act on R3, but they don't act freely on an R3. But there is always Z to the n tree where they act freely. So this is an example of groups acting on Zn trees. Also, I mean, it is interesting to know like which, so it was a lot of work, not extremely successful in proving that, okay, suppose we have two Zn free groups. Suppose we have Z1 and Z2 are Zn free groups. What happens if you take an amalgamated product or H&N extension? Like, is it also like Zm free for some other M? It turned out that like if you take amalgamated product over maximal abelian group, maximal of a cyclic group, which is maximal abelian in both factors, then amalgamated product is ZM3 for some M. It's a result of Martina and Rourke. Unfortunately, that's not true for, there is no such result for HNN extensions. There are always kind of counterexamples. So there are no good conditions when HNN extension preserves. I mean, there are good conditions if they are good. Like actually, we have a theorem that if you take an HNN extension, then it preserves, not preserves, it also ZM3 if the image of the cyclic group or even abelian group, if their lengths isomorphic. Because for HNN extension, what we need a group like G1, right, a subgroup C. Okay, and we take, and we have two embeddings like sigma of C and tau of C. We have an isomorphism from this to this, so it should be length preserving. Like the length of element C in G, the length of element sigma of C in G and tau of C, they must have the same length. Then the HNN extension will act freely on ZM3. But again, you cannot say if and only if, because you know, there are many ways to define length in G, and sometimes you don't know, so maybe there is a length preserving isomorphism, but you just don't know it. So that's, now other example of ZN free groups. I said that, so limit groups are ZN free. And it helps a lot because, you know, then like free group, so which is Z free. The good properties of a free group that there are clear cancellations, right? So since it is Z free, there are clear cancellations. You can always make a cancellation table like for product of elements. And you can do the same thing for limit groups. So this allows to solve many algorithmic problems. Basically, all algorithmic problems, like word problem, conjugacy problem, equations, and so on, and limit groups, we solve this using the fact that they are ZM free. And this allows basically to prove the decidability of the elementary theory of a free group, because you can solve a lot of questions about limit groups, which are very important there. Now, another example, Z and free group. For example, this is a non-orientable surface group of genus 3. This group is Z square free, but it is not R free and not fully residually free. So the class of Z and free groups, it's larger than the class of fully residually free or limit groups, and it's larger than the class of R free groups. There are many groups which are Z and free, but like not R free. And yeah, so like this is sort of if and only if theorem, which I necessary and sufficient conditions, which I mentioned. This is our theorem with Alexei Mesnikov and Denis Serbin. Basically, it says that any finitely presented regular, I won't say what it is, lambda free group, can be represented as a union of finite series of groups, where G1 is, so we start with a free group, and next one is obtained from the previous one by finitely many HNN extensions in which associated subgroups are maximal abelian, finitely generated, and associated isomorphisms preserve the length induced from GI. I was talking about length preserving isomorphism. So isomorphisms are length preserving. So like if the group is like this, it acts freely on. It is lambda free. And also every lambda free group, every regular lambda free group is like this. And another result that every finitely presented lambda-free group can be isometrically embedded into a finitely presented regular lambda-free group. So basically the description would be like this. So every finitely presented lambda-free group, we know that it acts on Rn, and also it is a subgroup of this, of the group obtained by this chain from a free group. Like it's isometrically embedded into a group like this, into so-called regular lambda-free group. So that's like the best description we have now for finitely presented lambda-free groups. For finitely generated, the problem is wide open. Like it's not known what they are. And okay, and now we mentioned some corollaries. So like since such a group, since finitely presented lambda-free group is a subgroup of that chain, using Basser theory about subgroups, we can say that any finitely presented lambda-free group can be obtained from free groups by a finite sequence of amalgamated free products and H&N extensions along maximal abelian subgroups, which are free abelian groups of finite rank. It is just by Basser theory, every subgroup of that chain, which I showed, like, is like this. But what we cannot say that every group obtained like this is lambda-free. So every lambda-free group can be obtained like this, but only like about regular lambda-free groups, we know that we know necessary and sufficient condition like for a group to be regular lambda-free. But they have still like finitely presented lambda-free groups. They have very, very nice properties. Like, okay, so for example, every abelian subgroup of such a group is free abelian of finite rank. And the rank is uniformly bounded above by the rank of the abelianization of the group. The group has finitely many conjugacy classes of maximal non-cyclic abelian subgroups. It has a finite classifying space, and the homological dimension is at most maximum of 2 or R, where R is a maximal rank of abelian subgroups. Then it is hyperbolic relative to non-cyclic abelian subgroups, so it's total relatively hyperbolic. And what else I wrote here? Now, it is every finitely present lambda-free group is biautomatic. Okay, I probably won't talk about right-angle arcing groups, but it is embeddable into, it's virtually special. Like there is a big, I don't have enough time to talk about this. So there is a like interesting class of right-angle arcing groups, and maybe just, so right-angle arcing groups, basically we have a simplicial graph, right? Right-angle arcing group is given by the generators and nodes of the graph, and relators are just commutativity relators. So if we have an H, V, W, then we say that V commutes with W. And right-angle arcing groups played a big role in this business of Weiss and Agel, that's the proof of virtually hacking conjecture, like so solution of this last problems from Thurston's problem list. And Weiss introduced the so-called group with a hyperbolic hierarchy. And okay, so we just saw that these groups acting freely on lambda trees, they have this hierarchy. And therefore they are virtually special. So they have finite index subgroup which is special in like Weiss definition. So it's okay. So hierarchy for a group G is a way to repeatedly build it, starting with trivial groups by repeatedly taking amalgamated product and H&N extensions. whose vertex groups have shorter length hierarchies. And the hierarchy is quasi-convex if the amalgamated subgroup C is finitely generated and embeds quasi-isometrically into A and B. And the hierarchy is malnormal if this is malnormal. I already defined malnormality today. And so the Weiss theorem says that suppose that G is toral relatively hyperbolic group and has a malnormal quasi-convex hierarchy. Then G is virtually special. Therefore, has a finite index subgroup that is a subgroup of a right angle arching group. And so that's exactly true for finitely presented groups acting freely on lambda trees. So they have this hierarchy. This is how they are built. They have this hierarchy, and they are toral relatively hyperbolic. So they are relatively hyperbolic with respect to abelian subgroups. And abelian subgroups are malnormal. So they are virtually special. And therefore they are subgroups of right angle arching groups. And that's probably, and then one can get some corollaries like from this, but I think I'll probably stop here. So this is a very nice class of groups obtained by free constructions and having nice algorithmic, like geometric properties and logic properties also. And the problem to describe finitely generated lambda free groups is still open. Okay, thank you very much.
Let's thank Olga for the entire mini-course.
I have a question.
Mm-hmm.
Yes.
How about word problem in these groups? Is it solvable or not? It's finitely presented.
Yes.
Lambda groups.
Yes, because it's toral relatively hyperbolic, so the word problem is solvable there.
And you said that the finitely presented is reasonable, but finitely generated is not. How about
generated? I don't know. Maybe the information that the group is finitely generated and acts freely on a lambda tree. Maybe this implies that it is finitely presented.
I
This
would
is
just wanted.
what I hope for, because this is what happened with R trees. Like Rift's theorem shows that you take finitely generated group acting freely on R tree, and this group happened to be a free product of surface groups and free abelian groups, so it is finitely presented. Like this is what I hope, but it's I don't know how to prove this.
So recursively presented doesn't make change.
No, it has to be finitely presented for our methods to work. The group either has to be finitely presented or it should be, I mean, basically some chain of adding relations should stabilize, but we cannot prove that.
So the relations must be good enough if they are infinitely many.
I mean, it's maybe the fact itself that it acts freely on a lambda tree, maybe it implies that actually it's finitely many or that they are good enough. Because it also implies some splittings, existence of some splittings with amalgamated products of each and extensions. But this has to stop. Like if this sequence of splitting stops, you guarantee that it's finitely presented. Like for example,
that's because the group without solvable word problem were built using H&N extensions, and you also
but you see, when you have actions on trees, then this is H&N extensions over abelian subgroups.
Yeah.
Like because they are certainly H&N extensions, but not over abelian subgroups.
I see. So they're much more rigid.
Basically, to solve the word problem in H&N extension, if you have abelian subgroups and if you have membership into this abelian subgroup solvable, then you can solve, like you have taken H&N extension of a group A over abelian subgroup A. If the word problem in H is solvable and if the membership problem into A is solvable, then you can solve the word problem into H&N extension.
Yes.
And then you do the chain, like of this.
Okay, thank you.
Unsolvable word problem, it's not abelian subgroups, which are age groups for each and next. Actually, in all relatively hyperbolic groups in general, the isomorphism problem is solvable, not only word problem. Conjugacy isomorphism problem is solvable. Equations are solvable. Even
Conjugacy?
Conjugacy problem is solvable, yes. Even equations are solvable.
Ah, I see. Thank you. Misha. We cannot hear you, Misha.
Any other questions?
Oh, I have a question, Olga,
Yeah?
about Judy's
Hi.
question. So for
Nice to see you, Eduardo.
groups acting on Rn, R3 and 3, so it's not known where they are coherent. Is that what you said?
It's not known
Whether they are coherent, if the finally generated subgroups are finally presented.
if the finitely generated subgroups are finitely presented. You know, I cannot remember now. So let's see.
Because for limit groups, that's the case, right?
Yeah, no, it is not known. Well, maybe it's known that they're not necessarily. But basically, from Girardel's theorem, I mean, I don't see why finitely generated subgroups should be finitely presented. But maybe they are, because they also act, but they don't act. Yeah, let me see. Yeah, in Girardel's theorem, so it is not known. I mean, there is no counterexample, because I thought that maybe there is a counterexample. No, it's not known. Because if there was a counterexample, we would not hope that group acting freely, like finitely generated group acting freely on an lambda 3 would be finitely presented, if there was a counterexample. But it looks like we still have a hope, so probably there is no counterexample. But it is also not known. Like, maybe you know something.
No, I don't know. No, but I see that there are results about amalgamation along cyclic groups that present coherence, right? So probably they, well, Danny White is the expert on coherence.
But then, so for which groups like coherence, what is the maximum class of groups obtained by like hierarchy?
Could you?
Virtually special groups, are they coherent?
No.
No, this is what I thought. Yeah. So no, I think coherence is not known. Like, but it may be like maybe.
Okay, thanks, Olga.
Any other questions?
I just want to mention one thing. You know, there is Higmann's theorem about the recursively presented group can be embedded into finitely generated groups. Yeah?
Into finitely.
Into finitely presented groups. So I know that for Lie algebras, we have this problem kind of first closed and then open. Years ago, you mentioned in one of your survey that this theorem for Lie algebra is not proven. Do you know anything new about this?
Wait a minute. You asking me?
I mean the theorem that a finitely recursively presented Lie algebra can be embedded into finitely presented Lie algebra.
But it's true, right?
But this is not known.
It's not known.
Okay, we forgot what we did years ago, because I think that in one of your survey with Sapir.
In my survey with Sapir, we said that it is true.
No, you said that the proof which existed at that time was not true. There was a proof.
Because I forgot now, whose proof was it?
That was Kukin's proof.
Ah, but that's not true, yes?
No, I think that you mentioned that was not true.
No, it's not. Cooking's proof is not true.
Yes, that's what you mentioned.
Ah, and there is no other proof.
And there was no other proof.
Uh-huh.
So it's this kind of wide open question for Lie algebras, because we don't have a good notion of H&N extension in Lie algebra. So I think it's interesting problem.
Yes, it is an interesting problem. I somehow forgot about this because cooking proof really is not true. Like,
Yeah.
I remember now. Yeah, but I
But
thought
there is
that it was
no
proof.
substitute.
Uh-huh. Yeah, that's an interesting question. Yeah.
Yeah. So the word problem is not solvable. That's other examples. But Higmann's theorem, that's what remains to be open.
Yeah, and probably because we probably could not save cooking's proof.
No.
Because we were thinking about this, like I remember, because sometimes things can be saved. And I think it was not possible not do this.
Unfortunately, this is a problem which is not solved. But maybe it's fortunately. There is another good problem to be solved.
Yeah.
Yeah, okay. My question is over.
So any other questions?
Okay, I just want to thank Olga for your very nice mini course.
Thank you.
Thank you for your
You told us.
attention. Like, I mean, people are so tired of Zoom's talk by now that it is like, it's nice to see people still.
Well,
Zoom
at least we have some difference. This is not a Zoom talk. This is a WebEx.
This is like, yes, this is WebEx. Why do you use WebEx? It's better than Zoom or?
Because our
The
university,
university has subscription to WebEx and not to Zoom.
Uh-huh.
actually, university has close connection with Cisco.
I see, okay.
And
Not
this
just
is
because of,
product. Yeah, WebEx is.
and therefore it had to choose WebEx because it's bound to Cisco.
Uh-huh, I see. No, it like looks like the quality is the same, and also several people cannot talk simultaneously like in Zoom. It's yeah. So so thank you very much for the attention, and I hope to see people in person.
We dream about this too.
It would be so great.
We will be so happy to have you for the fourth time in Rio, here in Newfoundland. Thank you very much, and let us thank Olga again.
Thank you.
Have a great summer.
Too. Yes, and I hope that maybe in the fall already it would be possible to travel.
Okay.
Have the vaccine. Like,
Bye-bye.
bye-bye.